So I'm going to show you just examples of what's going to happen. You're going to dive deeper when it comes to your homeworks, but at least you see some examples on how things are set up using the laws that you and I have already gone through and some things with proofs. Now, in proving set identities, we're going to basically, the De Morgan's example is frankly the best one. You're trying to see that two different set results two different set syntax end up in the same results. That's what we're after. But there's three different ways of doing this. There is the proof that each side of the identity is a subset of the other. Now remember, subset is equal to or smaller, so just heads up. We can use set builder notation and propositional logic to prove it as well. And then there's the membership tables, which frankly looks like truth tables. So those are the three examples that you're going to see here in a minute. So they love using De Morgan's for this because, again, here are our two different overall syntaxes that we're going to basically prove that the sets are equal to one another. Now, there's also two stages to this. So you're going to see two stages in many setups that we have here. And again, we have three different setups for this. So there's stage one and stage two. You're going to see that in each of the examples that we have here. Now, there's other laws that are going to get used in here that we're familiar with. We're also familiar with De Morgan's laws as well from previous setups and propositional logic or whatever that we've studied so far. So let me get into the first example that we have here. Now, when it gets into our overall set of notes here in proving our set identities for the first portion of this, you're going to notice the overall table is going to be set up. You're going to notice that our overall setup for this identity is going to look, well, pretty familiar, doesn't it? We're going to have our steps, we're going to have our numbered steps as well, and then we're going to have our reasoning for all of this. Now, again, the overall set that we're using for this, I want to say set, but the overall steps that we're using is doing the proofs that we've done before. By assumption, definition of a complement, and most, by the way, this one's mostly definitions. It's not a lot of the proofs that we've done before here. First, De Morgan law of propositional logic. So a lot of these are these particular setups that you and I are actually used to before and getting down to a solution. So all I want you to do for right now is digest this. That's about all I want for this. You need to look up the laws that we've had. We're using definitions of a complement. We need to know all of those type of things when it comes to the overall setup and answering in a proof-like situation. Our second example is the same basic idea, but again, this time we're using the second set of items that are in De Morgan's. So we're using that and going basically from top to bottom as we've done before in the tables before. By assumption, definition of a union, definition of a complement, and notice that each step we're just representing a small change from what the previous one was before. So again, here's the same idea, but this time we're using set notation as our overall set solution for this. So notice here's all the different set notations that we're doing. Now, by the way, a lot of it's very similar to what we had before. Definition of a complement, definition of our element is not within. These are all, a lot of these are definitions, so make sure you understand what each of these are that we've covered in this set of notes here. But that's the important part is, again, it's a set builder notation for this and proving the first part of De Morgan's. So again, go through each part of this, read what it is, and also make sure that you understand the overall setup. Here's part two of that, and it's almost just the opposite of part one here, again, using the set builder notation. And again, nothing crazy about what the definitions are. So you can think of this as almost a truth table using a membership table. You could think of this as being an and. So where we have 1 and 1, we get a 1 and then nothing else from there on out. And then we knot that to get our, well, zeros and ones from there. So that's pretty simple. And then we have the knots that we have, oh man, I missed those truth tables days, huh? And not bees, and then this you can use as an or. We have the ors As long as there's a 1 in there, it ends up to be a 1, and notice that both of them end up being similar. And that's our last way of proving De Morgan's. And by the way, this is doing both of them at the same time. There's our first set, and then there's our second set.